Okay, let me share my screen. All right, everyone can see it, just making sure.
Looks good, yeah.
Okay, great. Yeah, so hi y'all. I'm super happy to be here. I'm very excited to talk to you all about the science I've been doing. And yeah, I guess let's just dive right in. So I'll be talking today about spectroscopy of galaxies during reionization. So the epoch of reionization represents a really chaotic time in the early universe when the universe transitioned from fully neutral to fully ionized. And this happened before the universe was over 1 billion years old. And so this is really early in cosmic history. And so one way that this might have happened is shown through the simulation here, because I like pretty pictures when I'm talking. So what you're seeing as we're walking forward in time is these dark clouds are representing this neutral gas. I like to think of it kind of as a cosmic fog, blocking light from these early galaxies. And you notice as we go forward in time, the edges of these dark clouds start to dissipate. So something is suppressing this Lyman-alpha emission, or sorry, something is ionizing these neutral clouds. And so as we walk forward in time, if we were to follow the simulation all the way to the end, we'd have this bright, clear galaxy, fully ionized universe by about redshift 6, 1 billion years after the Big Bang. So another way to see this is through this particular graphical representation. So this time is increasing to the left on this plot. And so what you're seeing is, this potentially patchy reionization process where you'll have these darker patches, this start to form and get larger and larger until you get to this ionized universe at the other end. And so observationally, we have some evidence for the end point of reionization. We keep saying it's probably around redshift 6 or 6.5. And we kind of have some of this evidence from some of the things you see like on this plot on the bottom, where if you look at the escape fraction of ionizing ultraviolet light like Lyman-alpha as a function of redshift, you'll see that this escape fraction is increasing all the way up to redshift of 6. And then as you get to higher redshift, it just drops. So something is obviously suppressing this Lyman-alpha emission. And we have some other evidence for this as well, also using Lyman-alpha, where if you were to look at the fraction of strong Lyman-alpha emitting galaxies, where in this case, strong has been kind of arbitrarily defined to be 25 angstroms rest frame equivalent width. You can see that for the fraction of these strong Lyman-alpha emitters, it increases up to redshift of 6. And then as you get to higher redshift, again, something is suppressing it, it begins to drop again. However, as a note, not for the most brightest massive galaxies. So this is a really interesting point. So we do have this effect of Lyman-alpha being suppressed at redshift greater than 6 as we enter into the end of the epoch of reionization. But these brightest, most massive galaxies seem to be relatively unaffected. And so this really speaks towards what might be going on inside the epoch of reionization, this process, and maybe these really bright massive galaxies are indicative of overdensities where they've been able to ionize the neutral gas around them, allowing more light to escape. And so it's a really interesting questions going on, and the narrative is very much still relatively unclear. Overall, though, this does kind of highlight the importance of this ultraviolet line Lyman-alpha for being a really effective tracer for finding these high redshift galaxies and trying to peer into this epoch and see what's going on. So just to show you another animation, because I just find these really helpful, this is one I've made where we're just taking a model galaxy spectrum and applying a redshift. And I'm really just including this because I find it really poignant to see how when you get to redshift 6 and greater, there's nothing blueward of the near infrared. So this ultraviolet light is the first light we'd see from this galaxy, and it's in the near infrared. And so if you were to try to look at these distant galaxies, you have to start in the near infrared and then go to higher redshift or higher wavelengths, which is really hard. And so just kind of highlighting how challenging it is to try and enter into this kind of really high redshift science, and why these future telescopes are really going to do great with the kind of science we can do. So specifically for the work I do, I'm going to focus on the rest frame ultraviolet, like you might have guessed, specifically because while the rest frame optical is really important and highly studied at lower redshifts, I think the rest frame UV is really important because it contains a really awesome wealth of information about the physical nature and conditions of galaxies and the conditions of star formation, and a lot of really important information. So I just talked a lot about how useful Lyman-alpha is and how we use it a lot to peer into this early epoch in cosmic history. But for my science, there are complications with Lyman-alpha. So Lyman-alpha is this resonant line, so it's really subject to scattering, and it can be heavily attenuated by neutral hydrogen. So the redshift you would derive from Lyman-alpha can often be redshifted hundreds of kilometers per second from the systemic or true redshift for the source. And so you can see this really beautifully described in this awesome Lyman-alpha detection from Dan Stark's work in 2015. And so this asymmetric Gaussian emission line shape that you see here is this Lyman-alpha detection at epoch Reionization galaxy. And so you see the blue dashed line is the redshift we would derive for Lyman-alpha from this particular emission line, which is offset from the systemic location for this galaxy. And so you can actually quantify this offset in redshift space with the equation in the bottom left, describing the velocity offset from systemic. But mostly this just kind of highlights a need for some kind of line or detection that can trace the systemic for a source that is not attenuated by neutral hydrogen or outflows and really can represent the true redshift for these galaxies. Because once you get that information, you can start to do a lot more detailed analysis into the nebulae physics. And so because I specifically focus in the ultraviolet, here are some examples of some rest frame ultraviolet nebula lines that might be really useful for this work. This is a gorgeous Lyman brick composite spectrum from Alice Shapley's work in 2003. And so I've highlighted a few of these in red. I've also highlighted Lyman-alpha, of course. But something I really want to pinpoint, though, is this slightly less red color, this carbon 4 line I've highlighted, is definitely a useful line if you can target it, but it also has some complications because it's a resonant line itself. And so you can get some really fun nebulae physics if you get a lot of these lines detected for a single source. If you have to pick just one, though, for very high redshift galaxies that are expected to have very high ionization and very low metallicities, carbon 3 is your best bet, because for star-forming galaxies with those kinds of conditions, it's usually the second brightest line after Lyman-alpha in the ultraviolet. However, it is also important to note that for particular high redshift galaxies, if they're within the realm of where ALMA can look, telescopes like ALMA could potentially target their O3 and carbon 2 lines at very high, large wavelengths, which has happened for a number of galaxies in this epoch as well. So just so you know, there's a multi-wavelength approach, but specifically I will be focusing on the ultraviolet. So here are some examples of ultraviolet detections for systemic measurements in addition to Lyman-alpha for 5 different galaxies. And so we have 3 galaxies on the left that had Lyman-alpha detected and then carbon 3 detected. And then the top on the right is a carbon 4 and O3 detection with Lyman-alpha. And then on the bottom right, we have nitrogen 5 and helium 2 detected and then Lyman-alpha. And so these are 5 galaxies of redshift greater than 6. And there aren't many more that have these systemic UV tracers at these redshifts, because it's just very hard to do this kind of science. So the little that we have has actually taught us quite a bit. So what we've learned so far from these UV detections is that these star-forming galaxies at these redshifts seem to have these subsolar metallicities, very hard ionizing radiation, possibly young stellar populations, and possibly including binary stars or IMFs that extend up to 300 solar masses. And I'll show you a little bit more later in my talk about how we can start to pull out this information. But for the most part, this is the kind of picture we've been forming. But more UV detections, of course, from more galaxies would definitely help us paint a clear picture of this epoch. And ideally, more UV detections in the same galaxy to give us a better constraint on the nebula physics. So just to give you an idea of the kind of science you can do from rest UV spectroscopy of the single galaxy, I'm going to talk to you a little bit about a galaxy that's been near and dear to my heart for the past 4 years. All of the data I'll be showing you spectroscopy-wise, unless I specify otherwise, will be shown from the Keck Mossfire spectrograph. And so I know Caltech is really familiar with Keck in general, but just in case anyone's less familiar with the Mossfire instrument, Mossfire is this really amazing spectrograph on Keck, on the Keck 1 telescope, and it is, in my very biased opinion, the best near-infrared spectrograph, period. It has a configurable slit mechanism that allows you to look at up to 46 objects simultaneously, which is really cool. And it's configurable, so you can move it as you go. You can change your mask on the fly. You don't have to machine this stuff 2 weeks in advance, which is really useful. And also, because I'm hilariously obsessed with it, I co-designed a Mossfire mask on a mask. So if you would like a Mossfire mask, let me know and I'll point you in the right direction. So 1 year after Mossfire was commissioned, which was 2012, so in 2013, some of the first data that ever came out on this instrument was some work by Steve Finkelstein at UT Austin, where he looked at this particular galaxy and got a detection of Lyman-alpha for the source at a redshift of 7.51, which at the time was the highest redshift ever measured, which was really exciting. And it kept that position for quite a while until Mossfire and other instruments started shooting out higher and higher redshifts. But so later data totaling over 16 hours in the end from his then student Ente Zhang created this really beautiful emission line detection for this Lyman-alpha. And you can start to see with a 16-hour level of data, the asymmetry in the Lyman-alpha line, which is really exciting. And so from this data and from the ancillary candle spectrometry that we've had through this source, we can get some information out already. And so with this Lyman-alpha detection, we can get a Lyman-alpha rest frame equivalent width of 33 angstroms, which is pretty strong. We also have Spitzer-IREC photometry for this source. And so the Spitzer-IREC color 3.6 minus 4.5 is about 0.8 magnitudes for this galaxy, which at this particular redshift has O3, optical O3 and H beta in the 4.5 band, and then virtually nothing in the 3.6 band. So that color can be seen as a proxy for O3 and H beta equivalent width, which is really useful. But so with this detection, this is now where I would come in. So I take this Lyman-alpha emission. So we have a pretty good measurement of the redshift for this source. And then I go and try and target systemic line tracers. And so back in 2017, with about 5 hours of Mossfire H-band data, we got a detection of the carbon-3 doublet for this galaxy, which is really exciting. Just in case you're not used to looking at incredibly faint emission lines, here is a serendipitous O2 detection from a lower redshift galaxy at 7.237. And I'm mostly including this partly because it's very pretty, but also so to help you kind of calibrate your brain when you're looking at Mossfire data. So what you're seeing here is a positive trace in the center and then negative traces above and below. And so this is very unique to spectrographs like Mossfire that would employ a dithering technique as they're taking data. And so real things will have that feature, this positive trace and these negative traces above and below. And so now with that in mind, let's take that away. And so you probably now can agree that you see an emission line detected in the very center of both of these panels, both in the 2D and the extracted 1D. But I did mention that carbon-3 is a doublet. And very frustratingly, this galaxy is at the perfect redshift where the other part of this doublet is either on the skyline before or after that central emission line. And so by eye, it's very challenging to tell which part of the doublet we detected for this source. And so through some comparisons to the literature and just kind of best guesses, we assumed that the line we're detecting is the 1907 part of the doublet. However, for completeness, I will show you the other solution. So with that in mind, you can see the long dashed black line reaching both panels of this plot, showing you the location of the other part of the doublet on that skyline. And so from this, we get a systemic redshift for this galaxy of 7.5032, which then allows us to calculate a Lyman-alpha velocity offset from systemic of 88 kilometers per second, which is actually pretty small when we're talking about velocity offsets during the epoch of reionization. So it's really interesting. Now from this, you can get a total line flex estimated and calculate a rest frame carbon-3 equivalent width for this galaxy of about 16 angstroms, which is very strong for this kind of rest UV emission line. And so just for reference, that gorgeous Lyman brick composite spectrum galaxy I showed you earlier on from Alice Shapley's work at about redshift 3, the carbon-3 equivalent width for that source, it was maybe 3 angstroms. And so less than 5 angstroms is, and less than 3 angstroms is really common for, your quote unquote typical star forming galaxy. So 16 angstroms is considered very strong for this kind of line emission. But again, not really uncommon or unexpected for when we're talking about these distant early galaxies with young stars, very high ionization and very low metallicity. So doing some follow-up spectroscopy as part of a larger program, which I'll talk about in a little bit, I spent 4 hours with Mossfire J-band targeting the carbon-4 emission in this galaxy. And we got a really faint detection, which is really cool. So I'm bringing back this serendipitous O2 line just to help recalibrate your brain again. And also just to help those of y'all who aren't used to looking at faint stuff. Here are the 2 parts of the carbon-4 doublet. And so from this faint detection, we can get a carbon-4 redshift, which interestingly is different than both Lyman-alpha and carbon-3. So the carbon-4 redshift for this source is 7.5088, which gives us an offset from systemic of about 208 kilometers per second for carbon-4, which, as you remember from before, it is a resonant line, so it's not uncommon that it would not be at systemic. But what's interesting is that carbon-4 is actually more redshifted than Lyman-alpha for this galaxy by about 100 kilometers per second. And so this has a really interesting implications, some of which I'm still looking into. And I don't have time to talk about those during this talk, but if you want, I can talk a little bit about it at the end during the question session. But this is super interesting. Now, just taking the detections themselves, ignoring the velocity offsets for a second, let's compare the measurements that we have for this galaxy to other high redshift sources and analog sources at lower redshifts. So this is some really excellent work done by Schmidt et al. In 2021. And so what you're seeing here, colors of these plots, on these plots are representing the redshift. And so on the left-hand side, we're looking at the equivalent width of carbon-3 versus carbon-4. And then on the right-hand side, we're looking at the equivalent width of Lyman-alpha versus carbon-4. And so on the left-hand plot, our galaxy is located right around here, which is a little bit on the upper end of the carbon-4 emission, and kind of central as far as carbon-3 is concerned. So it's very in line with other sources, other analog and similar sources at high redshift. And so this is really always encouraging to kind of have it reconfirmed that it's doing exactly what we were hoping and expecting. And then here's where the source lies on the equivalent width for Lyman-alpha versus carbon-4. And so you can see, again, it's kind of on the higher end when it comes to carbon-4, but pretty much well-centered when it comes to Lyman-alpha. But an interesting note I'd like to add on this, this field is definitely changing every day as more detections come out and more papers get published. But as of this weekend, when I checked, this is the highest redshift galaxy to have both carbon-3 and carbon-4 detected in it. Like we have many galaxies that might have one or the other detected, but this is, we beat out a redshift 6 source to have the highest redshift for both carbon-4 and carbon-3, which is really cool. So now that we have all of these observational constraints, and we have some photometry as well for this source, now is the time to take all of our observations and compare to modeling to try and walk back any kind of inferred galaxy properties that we can. And so for the purpose of this work, I use the cloudy microphysical photoionization modeling code. In case you're unfamiliar with it, it's a really awesome code, a little bit of a learning curve, but essentially you really only need 3 basic parameters to get your cloudy models running. So you would need to describe the shape of the radiation field, and this could be a block body, a power law, a stellar population model, something that can describe your shape of ionization as a function of wavelength. The next you would want to describe the luminosity or the inner radius of the galaxy or the intensity of this ionizing light. And then finally, you describe the geometry. And with those 3 basic things, you can get some models out. Now, of course, there are additional optional parameters you can add. You can describe the nebula metallicity, elemental abundances, multiple radiation fields. There's like 200 extra things you can do. So use kind of lots of ways you can fine tune these models to do exactly what you want them to do, which is very exciting. But specifically for the models I'll be showing you in this talk, what I did was I decoupled the stellar and nebula metallicities, allowing them to vary independently. I also ran through a range of stellar ages, so 10, 30, and 100 million years. And then I also investigated a range of stellar population models. So I looked at both the BPAS single and binary models, and then the Starburst 99 models as well. And so to show you what those 2 look like, because I find this really fascinating. On the left-hand side are examples of the BPAS stellar population models. And on the right, we have the different IMFs for Starburst 99 models. And so right away, something I want to highlight is the main difference I seem to find in these sources is that BPAS definitely defines far more far ultraviolet light than the Starburst 99 models do. And so those are the kind of the key differences I've been finding. But another really important note is with the BPAS models, the binary population and spectral synthesis code, they specifically are including binary models. And so this helps, older populations live bluer longer. And so you can have a bluer galaxy that is in an older age. And so these are just some key things you can do to kind of tweak your modeling and kind of probe that parameter space a little bit better. So to show you some comparisons to observations, we're first going to look at a range of these kinds of models comparing to the equivalent width for carbon-3 that we detected, and then Spitzer arc photometry that I described before, which at this redshift is a proxy for O3 and H beta. So before I show you all the models at once, because it is quite a bit, what you're seeing here is I'm going to show you piecewise, and we're going to put it all together at the end. So essentially, with these panels, each panel's title describes the stellar population model that was used, with the upper mass limit for the IMF as well. And then on each plot, these line colors are representing the stellar metallicity of the models that are used. The line types are representing the nebula metallicity. And each of these lines has 11 models in it, covering a range of ionization parameter from -3.5 at the bottom left, increasing to the top right, where the top little point is -1.5. And so ionization is increasing to the top right is how you can think of it. So in this particular instance, all the models that you see right now are when we have fixed nebular and stellar metallicity. Now these are showing you when nebula metallicity has now been set to 30% solar. And here's when its nebula metallicity has been set to 50% solar. So you will see all 3 of these on the same plot. So here are 2 different stellar population models, just kind of to show you 2 different extremes. So on the left-hand side, we're looking at the BPAS models that have binary stars and an IMF that goes up to 300 solar masses. So very extreme population of stars. And on the right-hand side, we're looking at Starbase 99 models that have an upper mass limit of 100 solar masses. And so I mostly just want to show you these to kind of show you the change in how extreme you would need to get with these models to kind of match our observations. And you can see pretty clearly that on the left-hand side, we have a pretty good agreement with a range of different line colors and types that kind of reach into the space occupied by these stars, where the dark red star is our preferred solution. So if you were to, try and look at the kind of models that overlap, you can see on the left-hand side, stylus models that have 30% solar or less and ionization parameters log U of greater than -2.5 seem to be in pretty good agreement. But if you compare it to the right-hand side, you would see that within 1 sigma, only the most extreme lowest metallicity sources even began to creep into that space. And so they were really struggling to reach into the space to reproduce this strong carbon-3 equivalent width that we see. And also kind of reproducing that IRAC color as well. And so you can kind of just very clearly see that depending on the study population model that you use, or that input ionizing continuum, you're going to have agreement or you won't have agreement. Now, it is important to involve AGN models here, not only because it's a good thing to check, but also for this particular source, we had a tentative nitrogen-5 detection from some GRISM data, which for full completeness, we didn't see this in the 16-hour spectrum for Mossfire, but it could maybe be indicative of a weak AGN or an obscurity AGN or something like that. So here are some AGN models that we ran using Cloudy, and you can see that they do a really good job at covering the correct IR color space for a range of nebula metallicities. But they really overshoot when it comes to the carbon-3 equivalent width, which is pretty important, right? So they're just powering it a little too much. They're doing a really good job when it comes to the color, but they're not really doing a great job when it comes to these ultraviolet lines. So based on these data, we assumed or said that the study population models with the binaries and 300 solar mass stars seem to do a better job at matching our observations. However, if we fold in this new carbon-4 detection that we got last year, the picture starts to get a little more complicated. So the plot you're seeing left-hand side, models are the same kind of coloring, but now we're looking at the ratio of carbon-4 to carbon-3 versus IRAC color. And you can see that with these same models, only the lowest metallicity and highest ionization can now properly reproduce the dark red star, which is our preferred solution. So a ratio of 0.8 can barely be answered with the current modeling. And so this really opens a lot of interesting questions, especially when you compare it to what we just saw when you're just looking at the carbon-3 equivalent width. And so there's a lot of really interesting things that this tells us. One, now we need to change our modeling to see, well, what can we do to tweak these stellar population models to push them into that space? Is there anything we can do to make that ratio closer to unity and overlap more with this dark red star? Or is this really indicative that we need to think more about AGN again? Because if we do the same comparison with these AGN models, the same ones we had before, now there's a lot of overlap and agreement, which is really fascinating. And so just as a reminder, this is what we had before with the AGN models. But when you're looking at the carbon-4 to carbon-3 ratio, we have a lot better agreement. And so what this could potentially mean is maybe what the source is actually a weak AGN, or maybe it actually is a combination of predominantly star formation with some fractional contribution from AGN. And this isn't actually uncommon or unheard of. There was some really great work done in 2018 by Nakajima et al. Looking into these really great redshift 3 sources that had strong carbon-3 and carbon-4 emission, and really investigating if you could have a combination of star formation and maybe 8% fractional contribution from AGN, could you reproduce these strong lines? And what they found was, if you look at the solid lines, which are the star formation plus AGN, they do a pretty good job at covering a good range of strength for carbon-3 and carbon-4 over a range of low metallicities. And so I think at this point, it's pretty likely that what we're seeing in the source is a combination of the two, but really to properly figure out what's going on inside of the source, we will have to wait for space telescope spectroscopy, particularly because with instruments like NearSpec on JWST, knock on wood, we can get rest optical spectroscopy. And this is where the rest optical is very helpful, because getting O3 H beta, all of these other lines, you can start to do, the traditional BPT diagnostics to separate AGN or star formation. We can also get the slew of other lines. So what you're seeing here is, some model spectra put at this redshift for 2 hours on the prism is the big spectrum you're seeing. And so just with 2 hours, you can get Lyman-alpha all the way out to optical O3. And so not only would you get these optical lines, you can get a lot more UV lines potentially. And so not only could you better distinguish between what's the source of ionization in this galaxy, you get a lot more nebular physics you get to play with as well, which is really exciting. And then of course you can do medium or high resolution spectroscopy, which are these insets to break apart different doublets. But this is the kind of science we can start to do in now delayed, but hopefully, before the next fall. So yeah, so this is the kind of science you can do with a single galaxy. So now that we've seen what we can uncover or start to build a picture of for a single galaxy, let's repeat this process for a lot more galaxies. So my broader program, which is what I'm still currently working on, is using Keck Mossfire to target a slew of rest UV emission lines in galaxies at redshift 5 to 8. And so this program kind of came into being, it was something I was playing around with in the middle of observing on Mossfire one night, when the sparks of brilliance that might happen, or maybe in sparks of insanity, who knows. But what I was doing was I was redshifting different lines in and out of the Mossfire band passes. And then I realized that there's a sweet spot in redshift space, redshift 6.8 to 8, where you could have some number of rest UV metal lines in the Mossfire J band, and simultaneously, you could have some number of lines in the H band, which is really exciting. So what you're seeing in this image here is a simulated stack of Mossfire data with the Mossfire J and H bands showing what the coverage would be for redshift 7. And so redshift 7, you could get carbon-4, helium-2, and O3 in the J band, while getting silicon-3 and carbon-3 in the H band, which is really cool. It is important to note that we likely wouldn't get detections of all of these lines for a single galaxy, but that's okay because upper limits actually can give you really powerful constraints. As an example, from that galaxy we just talked about, we actually had the wavelength coverage for silicon-3. We didn't detect it, but we took an upper limit of it, and then comparing the upper limit to our actual detection of carbon-3 and comparing to that same modeling that you already saw, we get the following information. So this plot you're seeing is the ratio of silicon-3 to carbon-3 on the y-axis. And then we have log U, which is the ionization parameter on the x-axis. So another way to think of it is ionization is increasing to the right. And so if you look at the darkest red shaded region, which would be our preferred solution, only the lowest metallicity and really high ionization models reach into that space. And this was even before we pulled in that carbon-4 detection. And so even with just these upper limits, you can start to draw some really interesting constraints when comparing to modeling. And so with that in mind, this is the kind of science we could maybe do and start to build up a bigger sample of sources that have these lines detected in them. So to build this sample of galaxies, we used a number of different avenues. So the first one being taking advantage of the excellent work done by other people trying to do a similar kind of science. And so this is a compilation of work from Matthew et al. In 2017. And what I really want to highlight is this one over here, where these columns are just showing you these sources all had Lyman-alpha detected. And then people went and tried to take their rest frame metal lines to get any kind of detection they could. And you can see that for most of these columns, they are all upper limits. And I'm highlighting specifically in the carbon-3 column, the number of upper limits that you see. And so this just means, maybe it was the wrong telescope or instrument, maybe the observing conditions weren't the best. This galaxy might've been too faint for that source. But taking all of these previous and past observations, both successful and unsuccessful, we can fold those into our sample to try and retarget these sources using Keck Mossfire and see what kind of information we can pull out. So that was the beginning of the sample. And then the priority sample was definitely sources that already had Lyman-alpha spectroscopically confirmed. And a lot of my sources actually have come from some excellent work done by Inte Zhang and NASA Goddard. Definitely go check out his work from 2019 to 2021. This is just an example of 9 of the redshift 7 galaxies he's detected Lyman-alpha for. Really amazing work. And it's excellent to be a collaborator with him because he goes and does all this really awesome work, and then I get to use them in my follow-up spectroscopy. And then finally, because Mossfire can look at a lot of objects at once, we would fill out the masks with sources that have just photometric sources, no spectroscopic redshifts detected, but that would have really strong redshift solutions and very reasonable IRAC colors, and would be bright enough for Mossfire. And so what you're seeing in this plot is just an example of IRAC color versus redshift, where the open circles are some of our photometric sources. And they follow pretty well with some of these models that we're redshifting through the IRAC bands. So to show you some of our preliminary detections, we're definitely still working through the data, and shout out to Rebecca Larson, who I think is on the call, for an amazing job with the data reduction process. I'm first going to, again, for the third time, recalibrate your brain to what Mossfire data real detections look like. So just keep that in mind, the bright thing, the dark traces, the separation that they have. And so here are some of our tentative detections of these lines at redshift greater than 5. And so you can see that I'm not telling you what these lines are. because I want you to stay tuned. So this is preliminary as a note, but this is really exciting. So this is kind of a good proof of concept that this process seems to be working. We are getting some faint detections. Once we're done sorting through all of the massive amount of MOSFET data we have, hopefully I'll have a lot more really exciting things to say about this, and we'll run the same process of modeling that you saw in that first galaxy to see what kind of other information we can pull out. And this is all really well timed because we now have the advent of this next telescope that we'll be shooting into space one day, that we can use these sources as input targets for, which is really exciting. So kind of on the note of future telescopes and almost current telescopes, I'm going to briefly talk to you a little bit about the kind of science we can be looking forward to in the next coming years. So specifically with JW, I am part of an early release science program called SEERS, which is the Cosmic Evolution and Early Release Science Survey. And it is an amazing, massive collaboration that is looking to take advantage of NIRCam, NIRSpec, and MIRI to showcase all of the really awesome science you can do with those three instruments. And so what you're seeing here is the footprint of the EGS field and just kind of showing what potential observation strategy that we would have where you use NIRCam imaging, NIRCam GRISM slitless spectroscopy, NIRSpec MSA spectroscopy, and then MIRI imaging as well. And so by doing this in the EGS field, which has a plethora of data already taken through the candles imaging and a lot of other imaging campaigns and a ton of spectroscopy as well, the resulting beautiful amount of data that we're going to have adding in the GW data is just really exciting. And so just to specifically focus on spectroscopy, with NIRSpec for these data, we're expecting O3 detections, optical O3 detections, all the way up to redshift 9. So that would be about 40 objects greater than redshift 6 that we'll have these detections for. We're also expecting Lyman-alpha from about 20 of our redshift greater than 7 objects. We're expecting a ton of carbon-3 detections, which I'm particularly excited about. And then with the NIRCam GRISM slitless spectroscopy data, we're expecting about 50 O3 detections at redshifts 5.3 to 7. And then we're expecting O3 and H alpha as well at a range of redshifts. And so you can just start to see the kind of, even with just these single emission lines, like the kind of really awesome science you can start to do. And so if you're interested at all in learning more about what SEERS is up to, you can check out our website, which is seers.github.io. But I just wanted to show you this really awesome spectrum, which is a simulated spectrum where we have NIRCam GRISM spectroscopy on the left-hand side and NIRSpec spectroscopy on the right-hand side. And you can see that for redshift 9 source, we are expecting Lyman-alpha all the way out to O3, which is just kind of mind-blowing. Like I'm just remembering the hours I've spent getting a signal to noise 5 detection at redshift 7, and we're going to get this level of beautiful data from redshift 9 source. So I hope you're as excited as I am about this because it's going to be amazing once it launches. But additionally, not just JW is something we have to look forward to. There's actually also another amazing telescope on the horizon, which is called GMT. I'm sure we've all heard of it, but this massive telescope in Chile is going to also really revolutionize the kind of science we can do in a fraction of the time. So to show you an example, here is some really great data from Dan Stark's work in 2017. This is 4 hours with Keck MOSFire, where he got Lyman-alpha and the doublet for carbon-3 detected. And so just kind of pay attention to the signal to noise of these detections and remember it's 4 hours. And so we can get that same level of signal to noise in 4 minutes with GMT, which is the pros of going to a very massive telescope. It's just kind of amazing that you can get that level of signal to noise in a fraction of the time. And so if you want to do apples to apples comparisons, 4 hours to 4 hours, this is the level of data you can get from GMT with 4 hours for a H-band magnitude 25 source. And so you can get beautiful detection of Lyman-alpha, carbon-3, carbon-4, start to detect O3 and silicon-3. Like the kind of science you can do is just amazing. And so this paired with JW is really going to really revolutionize this very challenging subfield, which is really exciting. So yeah, so that is, I wanted to end a little early in case there's a lot of questions, but yeah, that's a summary of the kind of work I'm doing right now and what we have to look forward to. And thanks so much for listening, and I'll take any questions that you'll have.
Thank you very much, Taylor. Okay, just raise your hand, and if you have a question, and we'll call on you. got a quick question. So what do you actually end up learning about reionization with this large sample of Sears galaxies?
Oh, that's a great question. So you specifically mean with the GW data?
Yeah.
So I think one of the biggest things, here, I'll go back to that so we can stare at it. One of the biggest things will first be how many we find, and how far back can we see them? Because the current expectation is maybe we'll see galaxies at redshift 15. But if we can find galaxies at higher redshifts, that tells us a lot about the way that we're assuming reionization happens, and also galaxy formation at early times. But also, the number of galaxies that we see, the variety and the properties of these galaxies will also tell us a lot. But also specifically, there are some great geo studies or geo observations that are going to happen looking into overdensities, specifically at redshift 7 and I think higher than 9. And so trying to see if you can find these big bubbles of ionized galaxies that would also tell us a lot about the patchy reionization process, which I think now is kind of the assumed way that this process happens. Figuring out if what galaxy is actually contributing the most to reionization. Is it the brightest sources, or is it actually the fainter sources? And so I think it's going to very quickly come up with an answer, I feel.
Got it. Thank you. Okay, got a question from Cameron.
Hi, Taylor. Great talk. Thank you. I was curious, is James Webb really the only game in town with respect to doing these sorts of observations, or are there complementary? I mean, you talked about using Mossfire and some optical follow-ups to see some of the UV lines, but that's only out to a fixed redshift, right? So for these super high res, or super high redshift systems, is there any complementary way of detecting these, either in I don't know, the radio or microwave or something, that you'd be able to pick them up, or is it just going to be possible to do with JWST?
Yeah, no, so that's a great question. I definitely, JW has been on my mind because I've been also doing the job apps, but Mossfire will still be powerful. I think it shouldn't be thrown apart or thrown away. We definitely can still use Mossfire to target rest TV lines, and have them be filler targets for JW. But also what you mentioned with radio wavelengths, ALMA is a fantastic telescope just in general, but it's also been really powerful in getting detections of C2 158 and 0388 microns. And so those lines in particular have been really successful when people are targeting them at redshift greater than 7. The only downside there is, like for my redshift 7.5 galaxy, I would love to look at it with ALMA, but it's in Goods North. And so you are a little bit constrained on what ALMA could look at. You do have other instruments like IRAM, NOEMA in France, but that doesn't really, you can't really beat ALMA at those wavelengths. But ALMA is definitely going to continue to be powerful. It's going to continue to do awesome science at these redshifts. And I do think we can still take advantage of Mossfire and other instruments. But it is challenging, right? Like, it's instruments like the ones that are going to go onto GMT, and other massive, 30-meter class telescopes and JWST are really going to, I think, be the biggest things driving the science in the future, just because they're more capable of peering into these wavelengths that we need.
Okay, thank you.
Do we have any other questions? Okay, if not, then let's thank Taylor again for a very interesting and very clear talk. Okay, thanks again.
Yeah, thanks so much for having me. If you all have any questions, feel free to email me. Love to talk about this. So
Sounds good.